All right, let's take a look at section 2 here. We're talking about the ideal gas law based on what we covered in the first section, right? We want to, again, this will all be covered in the same quiz. We want to extend what we've started here. Okay, so remembering that we can combine volumes, we can use that to generate a balanced chemical equation. We have the value for N now, which is the number of moles of a particular gas, and we can use conversion factors, specifically the standard molar volume, to make calculations in that way. So we're going to take that one step further. We're going to start talking about the ideal gas law. So at the end of this section, I want you to be able to state the ideal gas law, derive the ideal gas constant. Using the ideal gas law, calculate pressure, volume, temperature, and the amount of gas when the other three quantities are known, right? And you'll actually use the ideal gas law to do that. Then, using the ideal gas law, calculate the molar mass or the density of a gas. And lastly, reduce the ideal gas law down all the way to Boyle's law, Charles' law, and Avogadro's law, and describe the conditions under which each applies. So here we go. So you've learned about the equations describing the relationships between 2 or 3 of the 4 variables: pressure, temperature, volume, and now moles, once we have Avogadro's law in section 1 of the text, that we need to describe any gas at a particular time. All of the gas laws that you've learned so far can be combined into a single equation. And no, not the combined gas law, because if you notice in Avogadro's law, which we introduced last section, the combined gas law does not take into account N, the number of moles of a gas. And so now that we have that additional value, we have one more equation to deal with, and it's called the ideal gas law. It is the mathematical relationship among all of these values: pressure, volume, temperature, and number of moles of a gas. It is stated as shown below, where R is a constant. It's the ideal gas constant.
The ideal gas law can be derived from Boyle's law, Charles's law, and Avogadro's law. Boyle's law states that, at constant temperature, the pressure and the volume of a gas are inversely proportional to one another. Charles's law states that, at constant pressure, the volume of a gas is proportional to its absolute temperature. From Avogadro's law, it can be deduced that, at constant pressure and temperature, the volume of a gas is proportional to the moles of gas present. Because volume is proportional to the inverse of the pressure, to the absolute temperature, and to the number of moles of gas present, it follows that it must also be proportional to the product of these three quantities. To make this proportionality into an equation, we need to insert a constant. We refer to this constant as the ideal gas constant and represent it with the letter R. Now, if we multiply both sides of the equation by P and rearrange slightly, we get the ideal gas law expressed in its most common form. The pressure of a gas times its volume is equal to the number of moles of gas times the ideal gas constant times the absolute temperature of the gas.
Now the ideal gas constant is going to be a little bit tricky, okay, but again, if you focus on the units, you can conquer this. In the equation representing the ideal gas law, the constant R is known as the ideal gas constant. Its value varies. It can have different numbers. Why? Because it depends on the units that you're using to represent pressure, volume, and temperature in the rest of the equation. Okay, so measured values for P, V, and T, right? Pressure, volume, and temperature, and N, number of moles of gas, at near ideal conditions can be used to calculate R. And so notice that we are using very specific units here. At ideal conditions, right? STP 1 atmosphere, right? At 1 atmosphere of pressure and at 0 degrees Celsius, which is 273.15 K, and we have 1 mole of that gas, right? Obviously, that gas is going to take up 22.4 liters, right? These are all ideal conditions, standard STP, ideal conditions. If we multiply all those numbers together, we get 0.082058. And notice that none of the units cancel. And so on the numerator, we have liters multiplied by atmospheres. And on the denominator, we have moles multiplied by Kelvin. And none of them cancel. And so in the value for R, we have to keep all of those units. And if I use a different pressure, for example, so instead of 1 atmosphere, I use 101.3 kilopascals, that's going to change the number, and it's also going to change the units that are in that ideal gas constant. So the calculated value for R is usually rounded to 3 sig figs, 0.0821 liters atmospheres over moles Kelvin. Use this value in the ideal gas law calculations when volume is in liters, the pressure is in atmospheres, and the temperature is in kelvins. Otherwise, it's not going to work out. The ideal gas law can be applied to determine the existing conditions of a gas sample when 3 of the 4 values are known, right? Pressure, volume, temperature, and number of moles. But always, with regard to the ideal gas constant, be sure to match the units of the known quantities and the units of R. And if the units of R don't match the units that you're plugging into the equation, do a simple conversion to make it so that whatever value and unit you're plugging into your equation matches the units for R, right? And here are some different values for R, considering different units for pressure, volume, temperature, and N. Now, we're not going to get varying units for temperature. It's always going to be kelvins. We're not going to get varying units for N. It's always going to be moles, right? Most of the time, we'll use liters for volume because milliliters is a pretty small unit when it comes to gas. But for pressure, we can have millimeters of mercury, we can have atmospheres, we can have kilopascals, we can have torr, we can have regular old pascals, right? We got all these random things. We have to make sure we're paying attention to what units we're using.
The ideal gas law is written as PV equals nRT. This stands for pressure times volume equals number of moles times the gas constant times the temperature. The gas constant is very important as it relates 4 measurable quantities: pressure, volume, temperature, and amount of gas. For example, if we take this constant volume box and add more gas to it, the pressure will increase. If instead we have a flexible container and add more gas, the box container will expand. The gas constant must have the units used by the other quantities in the equation. Some examples are R equals 8.314 liter kilopascals per mole Kelvin and 0.0821 liter atmospheres per mole Kelvin. Note that in both examples of gas constant, the pressure unit is different. This results in a different coefficient. Picking the right gas coefficient is important to make sure your units cancel out when doing calculations.
So let's see if we can do some problems here. What is the pressure in atmospheres exerted by a 0.500 mole sample of nitrogen gas, remember that's N2, in a 10-liter container at 298 K? So we've been given several things. We have volume, we have number of moles, and we have the temperature. And we're trying to find pressure. So we're going to use the ideal gas law, which can be rearranged to find pressure as follows. Right? Simply divide both sides by volume to get pressure by itself. That way we can plug and chug. So we substitute our values in. I make sure that the value I use for the ideal gas constant is consistent with atmospheres in liters, and that way I can have my answer in atmospheres and have liters cancel out. And so, plug and chug, I get 1.22 atmospheres of pressure. All right, guys, that's going to do it for this part of the video lecture. I will see you next period.